So basically, what we can see here on the screen, we can see the output on the screen here. So the first 8 are what I've connected as outputs, so they're the LEDs, and the second 8 are the inputs. So as we flip the switches over, you can see how the ones and the zeros are changing, and we can see there how the outputs are changing on the screen on that. So basically, that's in effect what I've done. You'll notice let's put the switches in here so you can see them. You'll notice that the top switch is operating the bottom LED. That's because they're reversed on the board, and I just wired it up and didn't think to check for that. This was done quite quickly. So some of them flash, some of them don't. It's just the way that I've put it on the software just to show the difference between how we could control different inputs and outputs. So that's it there on the screen. So what I thought I might do is just very, very quickly, there's not an awful lot of code behind these, and I've probably added a lot more in here than are really necessary, just so that it make it easier for anyone that wants to use one of these. It makes it easier so that they can, just changing a few things here, they can do it whatever they want with it. But basically what we're doing here is we have to put in what we call an input and output mask. So this basically is telling us that which pins are inputs and which pins are outputs. So we're defining that as far as our hardware wiring is concerned. Now, I said before we could have anyone using anything. It's just how we're going to do it from hardware point of view. Because I've got LEDs here, although we could read the LEDs if we really wanted to, or if we had something else switching these LEDs as well. But the way that I've set it up on the board for hardware, what I've done here is this is the lowest significant figure. So this first one here is port 0, input 0, or pin 0. So we're going up here. So they're all ones, which means their inputs look like a letter I. And these are all zeros, look like a letter O, meaning outputs. So our inputs are all port 0 from 1 to 7, and our outputs are port 1, 0 to 7, again on those pin numbers. So they basically, we just need whatever way you wanted to wire it. You might want 10 inputs and only say 6 outputs or whatever. You would just put that in there.
Why is there a B on that second digit?
This B here.
Yeah.
This B here is telling our code that this number is a binary number.
Okay.
You remember that sometimes you see here, we've got an OX here. That's telling us it's hexadecimal. This is telling us binary. Yeah.
Right.
Okay, so we've got this PCF1 address. I've called it a PCF1, which you'll see in a second. And that's our address that we've already got. Now, what I've put into this software is a little device which will tell us what our I2C address is, because it'll do a search right at the very beginning. So even if we haven't quite sure what we've done with our solder links, it'll tell us what addresses we've got. But we have to say here, we could have done this in software, but it's really lengthy, so I didn't bother. We have to tell it how many inputs we've got and how many outputs we've got. It could read this in, but this is all preprocessor stuff before we've loaded our loop or our setup. So trying to get it to do calculations at this stage in the coding is quite difficult. We can do it, but it's a real pain. So I just thought it was going to be easier not to do that. So these are what I've written here is the user configuration. That's what a user would need to enter into and just change those devices, those figures, and that's as far as they need to go, and that will basically work for whatever they wanted to do. These are all variables which we're setting off. We've got this thing, so we need to tell it what our inputs, and this is an array for our inputs, an array for the outputs, an array for the input values, whether it's a 1 or a 0, on or off, and again for the outputs. We've got PCF1 found here. So what we're going to do is going to make sure that before we try doing anything, so our code doesn't crash, it will only try and reading or writing if it can find it. If it can't find it, it won't read and write. We'll see that. This is just things to make our lights flash, which is using the millis function, which is a fairly common one. If you haven't seen it before, you'll see it in the code. We're setting a flash delay of 300. We can make that faster or slow. That's 300 milliseconds. So if we took it to 500, it would flash slower. And I also messed about, although I've not put this into here, I wanted to see how fast these will work. And it will do PWM at about 2 milliseconds, which is not great from a PWM point of view, but we could actually get it faster because we've only set the I2C at its slowest rate at the moment. So if we up to the I2C, we could get proper PWM happening on this, which is pretty good. So when we're using our two, this is a gotcha, by the way. Um, the examples omit to tell you that you have to use the wire library. So you have to put the wire library in, and you've got to call the wire library, begin the wire library, which I'll come to before you begin the PCF8575 library. So this is where we're creating our instance of our PCF8575. So this is, this is here is the, if you like, this is the menu, or the recipe for creating an 8575, and this is our instance, or the actual the cake that we're making from that recipe, the PCF we're making from this recipe. And we're making it to start at our PCF1 address, which we set up here by the user setting it there. Okay, so a couple of functions which I'm going to skip over for the moment because we're going to come back to those. We'll go back straight away down to our loop, which starts here. So what we're doing here is we're going to do our flash. This is just to make the LEDs flash, which I'm not going to go into any details, but it's there in the code. But here we're looking for, if we've found our PCF, then we're going to read it. And here, this is how we're assigning values to our inputs from our outputs. So what we're doing here is reading our PCF, looking at where our switches are positioned, what the value of each switch is, and then setting our output values depending on what our switches are. Then if it's found, we're going to write to it. If it doesn't find it, and it won't read, and it also won't write. So this will only actually do anything at all if it finds something, which is a bit pointless if we've only got one. But don't forget, with these, you can have 8 of these. That's 8 lots of 16, which is 128. So you can have 128 inputs and outputs. On top of that, if you used a PCF9874, sorry, 85, it's the 8-bit version, but you can get the 8-bit version in a different address range. So that'll give you another 96 inputs, or something ridiculous. So a total of 196 inputs, almost 200 inputs from these devices, which is more than anyone really would want to use. If we're using an ESP32, we've got tons of power behind that, which we can actually process all those inputs, no problem with the one device. We're going to have lots of cables going down from it, nevertheless. Okay, so that's there. So let's have a look at the setup we've got going on here. In our setup, this is where we need to begin our serial for our printed to the screen, and we'd also do our wire begin. This is important. This happens really early on. We're setting our I/O pins, which is a function which basically says how we're setting our indexes out for those pins, and what we're doing here is we're reading our input and output mask. One of the things that it has here is a thing called button. It's here in the code, so I can't remember where it is. Is it up here? There's one when we're reading. Well, let's go back to the reading, and we'll come to that. We're reading button 16 here, so it's PCF1. So we're setting a variable which is a 16-bit variable, and we're reading button 16. And what button 16 means is read every single input as an input and allocate it to a single integer, if you like, called ins, inputs. The button part of this means that it's going to ignore things that we've already told it are an output by that mask. So if we set, we've told it the mask that we've got, so it's going to ignore those outputs. So that allows us to read the whole lot. Likewise, when we're outputting, we're never going to write a 0 to a pin that we've allocated as an input. That means that if our input is from some sensor which is sending 5 volts out, we're never going to write a 0 to that, so we're never going to blow our sensor up. That's really, really useful thing, because it obviously makes it so that it's lock solid, and it won't blow our sensors up if we're going to do that. But the code here is in that on how to do that. So here we're writing our output pins. Because we've already set our mask, it knows all about it. So we don't need to worry about that. Our mask is set, I think, in our setup, which is... It's set button mask here, IO max. That's where we're doing it, yeah? So once we set our button mask, we're then writing here ones to everything. So in effect, what we're saying there is pull everything up so that when we can read something, we can read when it gets pulled down. So basically, that's what's happening in that particular part of the code. This particular part of the code here is something which you might have seen me do. I do this quite a lot. All we're doing here is we're going to go through n devices, a number of devices, setting it initially to 0. Then we're going to start at each I2C address, starting at 1, going all the way up to I2C127. And we're going to keep incrementing it each time we go through the loop. So start at 1, go all the way up. And then we're going to begin a transmission at that address. If we were to say an end transmission, it comes back to us with an error to say whether or not that transmission was successful or not. If it's an error, if it's 0, it means there's no error. So that means it's a successful transmission. It found it and it's there. So when we're successful, it'll say, yes, found something at address, whatever the address is, and part of this loop here. This prints a 0 just so it makes it look neat. So if I was to, this is still connected, hopefully, yeah. So if I was to clear the output on that, I have to do this so fast because it's let's see if I can stop it from scrolling, clear the output, and now go all the way down to, no, you know what I'm going to do? I'm going to reset it. Easier. And stop that and then move this all the way up to the top here. There we go, there. So right at the beginning of the code there, this is where this is here. So it's saying that it's found one I2C device. It's found it, and it's found it at 0x20, which is what we're setting. So if we look at that when we first run this, we can see that what connection our I2C is. So if that was 2.1, then we'll know that we need to make sure that that number is in our user configuration bit here at 2.1. So we would change that for 2.1 if that came back as 2.1. But that's what it's finding. But obviously, if we had 4 or 5 of these devices, it would list all the ones that it's found. We've seen that when we were looking at the Planck software. So basically, that's it. I mean, obviously, we'll put this code up somewhere. I haven't put it up yet, but we will, and we can do. Probably put it in somewhere. I don't know, where do we put things at the moment, John, for code?
At the moment, we'll either create a Merseyside Area Group GitHub, or whether you've got it on your GitHub, but it will
I'll put it in mine
on the knowledge base under the Merseyside Area Group. But this will become here's a Gizmo PCF8575 module.
But has anyone got any questions on what we covered, what I've looked at? As I say, if anyone would like to go into this in a little bit depth after we're done here, we could spend some time if anybody wants to.
I think it's probably going to be one of those things, Steve, where we've seen it, we've seen what it can do, we've seen that your code is there, but people probably need to go to your GitHub and have a look at it in detail, maybe have a go at it themselves, and then come back. Because as it stands at the moment, you know, it's clearly there and the principles seem okay, but obviously you need to sort of, you know how it is, you need to play around with these things for
very much so. Yeah. The beauty with this is that it's suited to any device. So even though that at the moment Arduino, the Nano and the Uno and all of these are all going through a period of change at the moment, and Arduino had now gone to be a private company, and there's all sorts of things happening. The ESP32 seems to be becoming flavor of choice. It's certainly, from what I've noticed, other people will have their own devices. Obviously, they prefer. But the beauty with this is with ESP32, there's loads of different devices of ESP32s. There's loads of different versions, and they've all got different pinouts. There's no real consistency behind them. The beauty with this sort of thing is that this will always be the same. So it doesn't matter what device we connect to it. The software is going to be the same for virtually all devices. So all we need to do is just to read the I2C on whatever device we do. And so that would then mean that even if we can change devices really quickly, really easily, and still have it working, and it will work for anything we want.